right, so this unit is going to be focusing on acids and bases, which are actually special types of solutions. So this is kind of almost a continuation of last unit, except these are some very special solutions. And in this podcast, we're going to kind of start learning about how acids and bases are special, a lot of the general properties and facts and how we can tell the difference between them. So let's get to it. First, we're going to start by focusing on acids. Now, it might seem a little weird that the first fact that we need to know about acids is that they taste sour, because we're never going to be tasting acids in our lab, but acids are all around us in the world, and especially in our foods. Anything that tastes sour probably has a large amount of some acidic substance in it, like lemons have citric acid in them. Vinegar is commonly used to add some acid flavor to more savory foods, but it is an acid, acetic acid to be precise. So, acids generally taste sour. They're also corrosive. You might remember this little pictogram from the beginning of the year, and that shows what corrosive means. It means it eats away at substances, whether that's the lab table or metals or your hand. You might have eaten way too many sour candies at some point, or some very acidic fruit, and your mouth started to burn or kind of hurt a little bit. Well, that's because that corrosion was starting to happen in your mouth, and you should probably stop eating so much sour stuff if you get to that point. But one of the primary things that that acids do react with are metals. They react and corrode metals, forming hydrogen gas. They also react with bases to form salt and water. We're going to be focusing on that reaction a little later in the unit. Now, all acids are also always electrolytes. They all conduct electricity because one of the fundamental things about acids is that they produce H pluses in solution. Those ions in solution is the definition of an electrolyte. So all acids are electrolytes, even though they're not all equally good at conducting electricity. They all can to some extent. Now, in class, I can show you this stuff called litmus paper. It's just some special paper, and if you dip it in an acid, it will turn red, or at least pinkish reddish color, to indicate that it is an acid. And we will definitely be spending a lot more time talking about pH next class, or maybe the one after that. And we're going to be doing some calculations with it, but over in kind of the basics, acids always have a pH less than 7. So we need to recognize that from the beginning of the unit, and we'll learn more about what that means and how to find those numbers later on. Now, quick little note that's right underneath this section with these 5 fundamental facts. We mentioned in fact 3 that acids produce H pluses in solution. But those H pluses are so unstable, if they're in solution, meaning surrounded by water molecules, they're actually going to grab on and combine into what we call the hydronium ion. It's just more stable for that little H, which is really technically just a proton, a single proton floating around in all these water molecules. It's going to grab onto there and be more stable because of it. So this whole unit, anytime we're talking about producing H pluses or finding the concentration of H pluses, we're technically finding the concentration of these hydronium ions. It's just a little simpler to think of them as those H pluses, since that's what's actually coming from our acid. So those are our 5 fundamental facts about acids. And now we're going to kind of talk about, well, what is an acid? And the truth is, this definition of what an acid is has changed over the years. So we have 2 definitions. The Arrhenius definition, which is the traditional, the older one. Originally, we defined acids as anything that dissolves or breaks up to form those H plus ions. So we could tell if something was an acid just by looking at it dissolved in water. Well, we realized over the ages with that definition there were some things that acted like acids, like they turned litmus paper red, but when we put them in water, we didn't see H plus ions forming. So what we realized, or what Mr. Bronsted and Mr. Lowry realized, was that those acids, it does come down to that H plus ion, but they called it a proton, in a chemical reaction between any 2 substances, not just the acid in water, that acids were going to give up that H to the other compound. And we'll come back to that idea at the end of this podcast, actually, with our conjugate acid-base pairs. But for right now, those are our two definitions. And they seem pretty similar, but you'll kind of understand a little better, I think, how they're a little different when we get to the base side of things and we see those two definitions again. Now, quick comment about our acids. They're not all the same strength. We have some acids that are strong acids and some that are weak acids. And if that sounds a little familiar, it should, because last unit, when we were talking about the basics of solutions, we learned that there were strong electrolytes and weak electrolytes. And the good news is that all of our strong acids are strong electrolytes, and all of our weak acids are weak electrolytes. So everything that's strong is a strong acid, or a strong base, I guess, are strong electrolytes. And we'll write that again when we get to our base side of things. But all of that means, and we talked about this when we were talking about electrolytes originally, is a strong electrolyte produces lots of ions in the solution, and a weak electrolyte produces very few. And so this is the same idea here. Our strong acids ionize completely, meaning they break up. Our HNO3 is breaking up into H and NO3 completely, 100%, or like 99%. Almost all of it is completely ionizing into these ions. And the more ions we've got, the more electricity we can carry. But also, here in this unit with our acids and bases, if you remember, because H pluses being produced is what makes something an acid, the more we break up and the more H plus ions we make, then that's going to make us a stronger, more acidic acid. Our weak acids generally have very low ionization. So our H and F that are starting together do break up some, but the bar that they set is saying, well, okay, a weak acid is going to only have 5% or less breaking up and ionizing. So 5% of our acid is going to exist as ions. The other 95% is going to exist as our original molecule with the H and the F still stuck together. So that means even if I put the same number of moles of my two acids into solution, then my H and NO3, my strong acids, are going to completely break up into two separate ions every single time. And here only about 1 in 20 will break up into those ions. Most of them will stay together. Means that they don't produce as many H pluses and they can't act like acids as well as the things that make more H pluses. Now we do have a list of the most common acids that are strong acids and then weak acids. And these are actually all of the strong acids. They're pretty rare to be strong. Everything else is a weak acid, and these are only a few of the examples of weak acids. There's lots and lots and lots of other ones out there. Now, you do not have to memorize those until, or unless you take AP Chem, but just recognize that we do have some listed out here. If for any reason, maybe in a worksheet, you need to list some out as examples and talk about them, then we've got a few examples here for you. So that's our acid stuff. Let's talk about bases for a minute. And most of these are going to be very similar things we talk about, but bases are kind of sort of the opposite of acids. So instead of tasting sour, bases taste bitter. And if you're not quite sure what the difference is, think about dark chocolate, or if you've ever bitten into the rind of a banana or a lemon or an orange, not the fruit itself. The fruit is sour, but the rind is very bitter, and that helps keep insects and stuff out. Almost anything that has a really thick rind on it is going to be fairly basic there. And if you bite into it, it's different. It's not sour. It still makes your face kind of pucker up, and it's unpleasant, just all on its own, but it is different. And a lot of people don't like dark chocolate because of how bitter it is. But if you do like it, then you're fine. Like, it's not as overwhelming as like biting into the peel of an orange or banana. Now, when these are in solution, they are slippery. So soaps are actually slightly basic. They have that weird slippery feel. And we're not going to be putting our hands in very many bases in the lab, but any of our bases would also have that weird kind of slippery feel, more than just wet, but almost slimy or slippery there. And we said that acids are corrosive, which means they eat away at substances. Bases aren't corrosive, but they are very reactive and they can be harmful. So we still need to be careful of our bases because they are caustic. Now, like we said before, bases and acids do react with each other. So here we've mentioned that bases react with acids, and they still form that salt and water, and we'll focus on that a little more later in the unit. Bases, just like acids, are electrolytes. They all conduct electricity because they produce ions in solution. It's just that our base ion is the OH, hydroxide ion, when it goes into solution. If we dip litmus paper in bases, then it tends to turn blue, and bases tend to have a pH greater than 7, or I actually like to think of this as a pH that is bigger than 7. And the reason I like that is because bases have a whole lot of words and descriptions here that are starting with B. So bases are bitter, and they turn litmus blue, and they have a pH that is bigger than 7. So that makes it a lot easier for me to remember all of those random base facts if I keep thinking about bases, bitter, blue, with big pHs. So those are our 5 fundamental facts about bases. Now to get into those definitions again, Arrhenius, like with our acids, defined our bases as what they form in water. So bases are substances that dissolve or break up in water to form those hydroxide ions. But Mr. Bronsted and Lowry came along and said, no, really what they are substances that accept protons and those H pluses in a chemical reaction. So here you can better see the difference between these definitions, I think. Arrhenius defined things by what they form just in water all by themselves. Bronsted-Lowry defined them as what is happening to our proton, whether they're giving and donating that proton like our acids do, or accepting that proton in our chemical reaction. So definitely different definitions, and you can see that more differently here because it's not just all about H+. Now, we do still have strong bases and weak bases, just like our acids, and they are only different based on how much they dissociate and break up. Strong bases dissociate completely. Weak bases only break up a little bit and dissociate less than 5%. Now, weak bases tend to need water's help in order to dissociate. So here we see NH3 is going to be accepting a proton, getting another H here from our water. And you can see that thanks to that water, it is technically producing OHs in that solution, but it's not bringing those OHs with it. It needed some help getting there because it's just a weak base. It's not as strong as these strong bases over here. Now, once again, these are all of our strong bases. We don't have very many that are super duper strong bases. It's only group 1 and 2 metal hydroxides, and not even all of group 1 and 2 metal hydroxides. Then we have some examples of some weak bases over here, and there's lots and lots and lots more. And you can see that our weak bases tend to not have their own OHs with them, those hydroxides, but they can. Something like gold hydroxide is a pretty weak base, and so even though it has that OH on it, it just doesn't tend to break up into that AU and OH piece, so it is weak.